Dear colleagues, dear organizers, dear guests, my name is David Mondartsev from Almaty University of Energy and Communications, Republic of Kazakhstan. On behalf of the co-authors, I will present the research results outlined in our paper in a presentation prepared by corresponding member of Bulgarian Academy of Science, Professor Hristo Veloev. It is of interest the design of and manufacturing of hybrid porous surfaces with a hybrid micro-nanoscale. Such kinds of surfaces can be considered future technological products. They become more compact, integrated, and multifunctional, able to operate with higher thermal loads. Therefore, we are developing nanoscale and microscale porous structured surfaces in the form of integrated mesh structures with coatings from natural mineral media, which are examined in the present study. The diverse tasks that were solved in the study for various devices of thermal power units, choice of heat carrier, consideration of its circulation type, choice of geometry and material of heat transfer apparatus and intensifiers, operating conditions of the type under pressure, vacuum, energy supply and type system orientation are described in sufficient detail. The conducted studies allow to give recommendations on the choice of a heat carrier, take into account its circulation type, determine the geometry and material of heat transfer apparatus and intensifiers with respect to the operating conditions of the system under pressure or vacuum, energy supply and type, and the orientation of the system. To control energy processes, it is proposed to separate the total energy into two components: the energy of a heat wave and an explosive generated steam nucleating heat, and the energy of a compressed steam flow, which is also important for modeling an analogy of boiling processes in the pores of a structure. Figure 1 also shows the design technique of porous system as applied to the designed devices of thermal power units. The conducted studies in many references allow the introduction of coolant liquid, housing material, and structure, the type of porous coating, the calculation of heat transfer, resistance, thermal stresses, and provision of the economic and environmental assessment. A promising thermal device for the reconstruction and modernization of turbo foundations are considered the rocket-type burners with high-temperature supersonic pulsating detonation jets, also called flares. Further development of the cooling system of the combustion chambers and nozzles is required in order to increase the reliability of the heat-loaded, highly accelerated elements of their structures. The designed combustion chambers and nozzles are also applicable for gas turbines as shown on Figure 1. Attempts for modern designers to design power units, including gas turbine units, is associated with the undeniable advantages of the detonation method of fuel consumption. By the way, scientific and design studies encounter two actual problems: how to implement a safe and reliable method of detonation combustion, and how to provide highly accelerated operating modes of combustion chambers and supersonic nozzles using the most advanced high-intensity cooling systems. To enable the detonation operating mode of power units, the most promising way is the design of supersonic nozzles with a shortened diffuse part. The cooling system is applicable for tools designed for cutting concrete and reinforced concrete, and especially for firejet burners installed in whirling thermal drills for turbo foundation works. In the case of using a capillary porous cooling system in thermal drills, firejet burners designed for drilling blast holes and burn holes, the scheme changes slightly due to a different arrangement of arteries. The cooling scheme is also applicable for air-cooled burners, benzo-air and kerosene air. In this case, the consumption of compressed air, which will be used as an oxidizing agent only, is reduced by 1.5 or more times. The capillary porous cooling system of such burners is highly effective and can significantly increase the life of the combustion chambers and nozzle apparatus from 100 to 150 hours to 500 and 600 hours. Due to a significant reduction in water consumption, refusal of pumps, high reliability of the system, design simplification, and low operating costs, the annual economic effect per burner equals at least $200 to $300. A significant drawback of the water system is the need to supply water under high pressure, as shown in the presentation. The nozzle and the combustion chamber of the burner will be destroyed immediately as soon as the water pressure in the line drops. To ensure high reliability, the water flow rate is assumed to be high and depending on the burner capacity ranges from 0.2 to 3 and more kilograms a second. In order to eliminate the indicated drawbacks to ensure high efficiency and reliability, a capillary porous cooling system is proposed on Figure 2. It has high technical characteristics, reliable and easy to operate. At the same time, in operating mode, the consumption of cooling water is sharply reduced by tenfold. Figure 2 shows a device for cooling the nozzle 1 and the combustion chamber 2 of a fire jet burner covered by a capillary porous body 3, the ends of which is connected to the artery 4. The capillary porous body 3 and the casing 5, which at the bottom with a gap covers the chamber and nozzle, protecting them from mechanical damage and at the same time protecting the personnel from burns, are tightly against the perforated tube of the artery 4. The cooling agent is supplied from artery 5 through structure 3 to the cooled surface of the chamber 2 and nozzle 1. The gap formed by the casing 5 and the chamber provides the active removal of steam due to its ejection of the supersonic high-temperature gas jet flowing out of the nozzle. The cooling agent is supplied from the pressure tank under a slight overpressure, as shown on the presentation. Its consumption is reduced by 60 to 70 times since heat is diverted by the steam generation heat. The capillary pore structure is easily removable, as it is enough to unscrew it from the distribution head together with the combustion chamber or loosen the screws 7 and remove from the chamber. A very small water flow rate, for example 3 to 4 times 3/3 kilograms a second for a kerosene oxygen burner instead of 0.2 kilograms a second, allows steam emissions into the atmosphere, which greatly simplifies the system and its operation. For comparison, we present interference patterns of capillary porous coatings made of the most tough rock, granite, with porosity that equals 5%, and the viscous rock, tuff, with porosity that equals 30%. On Figure 3, we show the holographic interferograms of tuff coating displaying the state of the surface every 6 seconds with a heat flux of 15 watts. The loading of the sample was made from the condition fixed from time 126 seconds to condition 180 seconds. Both coatings can be useful depending on the properties of the wall material in order to create two media with significantly different acoustic stiffness values and thereby provide control of the heat wave penetrating the cooling surface of the combustion chamber and nozzles that are shown on Figure 3 and 4. The analysis of interferograms of deformation and thermal stresses showed the following. The expansion of the coating sample occurs firstly around the heat source and then throughout. The deformation of the sample volume depends on the distribution of the temperature field created by the heat sources and the resulting thermal stresses on the surfaces and in the body volume. Figure 4 presents photographs of the granite coating every 6 seconds after the start of simultaneous heating from three sources with a total power of 7 watts. Figure 5 presents photographs of a marble coating under the same heating conditions as in Figure 4, a comparison of the deformation pattern of holographic interferograms and thermal stresses on interferograms obtained by the optical polarization method reviewed their analogy. which indicates the relationship between surface and underground processes. It was revealed that samples with low porosity, granite, are in a more stressed condition compared to viscous and porous media as shown on Figure 3. A two-fold increase in the heat flux power led to an up to three-fold increase in their surface deformation, while for samples with high porosity deformation, increase was only by half. The number of interference bands per unit length is higher for coatings with low porosity values, which means the presence of large thermal stresses in turn the growth rate of which increases along with heat load increase. Interferograms made it possible to detect not visible defects and cracks, as well as large inclusions in which area the equal deformation lines were winding. The type of thermodynamic screen is selected depending on the cooling surface material, taking into account the acoustic stiffness coefficient of the contacting medium. The thermodynamic screen can be installed independently or in conjunction with screens containing a cooling tank with fitting. These studies are important for upgrading and extending the life of thermomechanical equipment. Due to new thermal devices with porous coatings, the likelihood of cracks development coming from the reflected wave in nozzles and combustion chambers, as well as during the modernization of turbo foundations of power plants, can be reduced. Devices allow to create powerful thermodynamic screens for detonation, high-temperature jets, preventing cracks development, and are selected depending on the material properties of the fence surface. Holographic interferograms illustrate the concentration of deformations and thermal stresses in the solid under thermal loads up to 2.1 times 10^6 watts square by square meter. Capillary porous and flow-through burners cooling systems have shown high efficiency up to the limiting condition of the metal of combustion chambers and nozzles. If you have some questions, you can contact with me by email. Thank you for your time. That's all.